Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hello, welcome to Physics with Beth and Beth. I'm Beth, and we're in that AP Physics 1 curriculum, Unit 7 in Oscillations. You'll also hear teachers and professors call it simple harmonic motion. It just means that constant back and forth motion. Today we're going to be talking about springs. The last video that we posted, my colleague and friend Beth talked about the period of a pendulum. Today we're going to talk about the period of a spring, and it's going to look very similar. By the way, both of these are on your equation sheet for the AP Physics 1 exam. They look very similar, 2 pi times the square root, but what's different is what's under that square root. For a pendulum, it was the length divided by little g. For a spring, it's the mass in kilograms divided by the spring constant, which is a Newton divided by a meter is the unit on that spring constant. We're going to remind ourselves that a spring constant means the stiffness or the loosey-goosiness of a spring, I like to call it, and it will be unique to that spring. You won't have a different spring constant unless you switch out springs. Now, over time, a spring can lose its springiness, pun intended, but typically for these problems, if you're going to change the spring constant, you have changed the spring. All right, it's going to be unique to each spring. So then let's remind ourselves what period is. Period is the time it takes to make one cycle. I have a spring here, and I'm going to just stretch it down. So I'm going to start right here where it's stretched down. It's going to go all the way up to max compressed, and then it's going to come back down to where I stretched it. That would be one cycle. So the period would be the time it takes to make that one cycle. Okay? All right, perfect. We're going to talk about some concepts on this. All right, when we increase mass, we want to know what happens to that time it takes for one cycle. When we increase mass, that's in the numerator, so then that means it's going to cause your period to increase. An increase in period means an increase in time for one cycle, meaning it's going to go slower. All right, so when we increase mass, it's going to increase your period, which means it's going to be slower because that's more time for one cycle. All right, now we have, if I decrease mass, then that's going to decrease my period because that's in the numerator. That's going to decrease my period. That means less time. Maybe instead of 2 seconds, it's now 1 second to complete one cycle. And that means it's going to be going faster. So when we talk about mass increasing, we said that it increases the period, and that means that it increases the time per cycle, meaning it moves slower. So just as a real quick demo here, we have our spring. If I were to pull down on it, it's moving pretty quickly. If I take mass and I add mass to the bottom of this, it's kind of nice to visually see how slow this moves. So again, increasing mass increases period, which means increases the time it takes for one cycle. All right, and then the same when you decrease mass, I've taken the mass off now, it's going to be moving a lot faster because it decreases the time for one cycle, which is the period. Now we're going to look at this K value, our spring constant. When we increase the spring constant, that's in the denominator. Those are inversely proportionate. So when I increase my K, I am decreasing my spring. So I'm going to decrease, when I say spring, decrease my period of the spring. And that means it's going to go faster. We're going to have less time for one cycle. Now, when I decrease K, that's in the denominator still. When I decrease K, that's going to cause my spring constant, that's going to cause my period to increase because they're inversely proportionate. All right, well, when it increases, that means more time for one cycle, and that means this thing is going slower. These are good things to know. Now, let's talk about length. Length definitely affected your period of a pendulum. Length is not in the equation, so it does not, the period will remain the same. It's not in the equation. The length of your spring, if I had a longer spring, let's say I had a longer spring and it had more coils, Down here, it wouldn't affect its period, actually. All right, now let's talk about the mass for a pendulum. So the mass for a pendulum, we said, hey, in the last video, my colleague Beth said mass didn't matter. If you put more mass at the end of your ideal pendulum, it won't matter if we're ignoring air friction. All right, the same, but that's not the same for our spring. You increase mass here and it does affect it, and we've talked about that. Okay, so now let's just do a problem really quickly. We have a spring with a frequency of 2.5 hertz and a mass of 0.50 kilograms. We want to find the period, the angular frequency, and the spring constant for this spring. Now we're going to remind ourselves that angular frequency, we've talked about this. Angular frequency is measured in radians per second. Okay? It is related to our normal frequency in hertz if you take that frequency of hertz times 2 pi. So we said, hey, wait, angular frequency is one cycle, that 2 pi represents one cycle, and the time it takes to make that one cycle. It's a rate, radians per second. All right, and we said, oh, but wait a minute, we know that frequency is equal to 1 over period, they're inverse, or period is equal to 1 over frequency. We've said that in an earlier video. We talked about that relationship. So if 1 over t is frequency, I have a 1 over t here, I'm just going to put in my frequency, I get 2 pi times my frequency. So listen, frequency is in hertz, which is 1 over a second, but we've honored our scientist with that unit. And we're going to see that frequency and angular frequency are very similar. It's different units. It's kind of like if you're trying to, a similar, I think, thing to think about is if you're trying to convert feet into meters. There's a number you have to multiply to do that. Well, in order to convert frequency into angular frequency, you multiply by 2 pi. Okay? Now, there is also, we need to talk about another equation that you need for angular frequency. All right, for angular frequency, maybe they don't give you the frequency in hertz. They give you mass of your spring and the spring constant. And you're like, well, how am I supposed to get angular frequency if I only have these two numbers? Because neither mass nor spring constant are in this formula. All right, so this is how you do it. We know that angular frequency, we just said, was 2 pi over the period. Okay, well, I'm going to make it 2 pi over the period. I see the period of my spring is 2 pi square root of m over k. So I'm going to sub this part in for t here in the denominator. So I have 2 pi, and I'm going to put 2 pi square root of m mass over spring constant. Okay, well, my 2 pi's cancel out, and I end up with 1 over the square root of m mass divided by spring constant. We can simplify that down. So now we know that the angular frequency of a spring is equal to the square root of k over m. Because that's in the denominator, you can flip that. All right, that fraction, and you end up with spring constant over mass. So now, if they give you the frequency of a the frequency of a spring in hertz, you can use this equation. All right, if they give you the spring constant and the mass of a spring, then you can use this equation. If you have frequency and you have spring constant and you have mass, you can use either one. It doesn't matter, you'll get the same answer. Okay, perfect. Now we're going to just continue on really quickly and do this problem. I have a spring with a frequency of 2.5 hertz, so we know frequency is equal to 2.5 hertz. And a mass of 0.50 kilograms. First thing they want is period. Okay, well, here's the other thing. We said, hey, period is equal to 1 over frequency. So I'm going to do that. Period equals 1 over frequency, which is 1 over 2.5 hertz. So my period is 0.40 seconds. Okay, and you're like, well, why didn't you use the formula that we've been talking about, the equation? Because I have my mass, but I don't know my spring constant yet. So I can't use that equation. But I do know that there's another equation for period. Okay? Now I'm going to find my angular frequency. Oh, well, I know this. Angular frequency, I still don't have my spring constant, so I'm still not going to use that yet. I don't know my spring constant. They've asked for that last. But I do know that my angular frequency is 2 pi times f. So my angular frequency is 2 pi times 2.5 hertz. And that's going to give me an angular frequency of 15.7. And remember, angular is in radians per second. So I have the second part done now. Third, they want spring constant. Okay, now I'm going to be using the one on my equation sheet, where period of a spring equals 2 pi square root of m over k. That's going to be 2 pi square root of 0.50, because that's my mass, over k. And I already know my spring period was 0.4. So I'm putting that in. Okay, I'm going to divide both sides by 2 pi. And then, and actually, let me solve this with an expression first, and then we'll plug in everything. So I'm going to divide this period of the spring by 2 pi first. So I have period of a spring divided by 2 pi, and that's going to equal the square root of m over k. All right, I'm going to square both sides because a square of a square root just leaves what's underneath. So I'm going to square both sides. All right, I'm going to get t squared over my 2. Don't forget the 2 does not just go to the pi, it goes to the 2. So I have 4 pi squared equals m over k. Because when you square a square root, you just end up with what's under the square root. I'm going to now multiply by k. So I get t squared times k over 4 pi squared equals m. But remember, I'm looking for k. I'm going to come all the way over here, and I'm going to say, okay, I'm going to have k equals m times 4 pi squared over my period squared. All I did was multiply both sides by 4 pi squared, and I divided by my period squared. And you get this expression for k. Now I can plug in numbers. The mass was 0.5, we have 4, and we have pi squared. Our period was 0.4 squared, and you get k is 123 newtons divided by a meter, I believe. All right, that's how you do that problem. Now again, I already knew my, now that I know my spring constant, well, I just found it. I just found my spring constant was 123. My mass was 0.5. If you take the square root of that, guess what you're going to get? You're going to get an angular frequency of 15.7. If you were to take 123 divided by 0.5 and take the square root. So it doesn't matter which one of these you use. What matters is what variables you have to know which one to pick. Okay, that's it. That's the period of a spring, some concepts behind it, and when it's slower and when it's faster, just think about that relationship between the numerator, masses in the numerator, and the spring constants in the denominator. And you guys, we are so close to being to our very last unit in AP Physics 1. You're doing great. Hang in there. You are almost done. All right, the AP exam is approaching. So, warning, as they say. So anyway, you're going to do great, and hope you enjoyed this. Hope it helped. If you like it, give us a thumbs up. If you haven't subscribed, we would love for you to do that, or pass this on and forward it on, share it with your friends, your peers in physics. If they're helping you, we would love to help others. And thank you for watching. Happy physicsing.